photo, you see it's ice in Greenland that has been accumulating what the scientists call light-absorbing impurities. There's soot, there's dust, and a new frontier in science, there's also microbial activity. And there's a feedback there that we don't fully understand. But I wanted to start off fast-forwarding to the present. Today's story is about fire in the Arctic. This is tundra burning in Alaska. And climate warming has brought an increased fire season. Tundra fire is not unnatural, but if climate's warming and this fire season's getting longer, that's what sparked the idea about a new project, a campaign. We're actually trying to crowdfund a science expedition to Greenland, the second largest ice sheet on the planet, on the world's largest island. I like to call it the world's smallest continent. It's a dome-shaped ice sheet, 2 miles thick. It contains ice older than 120,000 years. It's accumulating snow net at the highest elevations, and it's melting around the edges. And that's normal for any glacier. The story for me began with 11 years of installing and maintaining a network of automatic weather stations on the inland ice. That was during my graduate studies at the University of Colorado. And a number of those stations are still running today, about 17 years after installation. In 2002, the story got a lot more interesting than the glaciology that I was taught, that taught us that the ice sheets had a frozen bed. And it just took some observations to realize that all this surface melting that was occurring was making it down to the bed. And through these passages that we call moulins. A moulin is a passage that water drains down through the ice sheet. And because water is an incompressible fluid, a mile of ice can glide on this water, and that accelerates the ice sheet 100% during the summertime, even more. And this was an epiphany in science in 2002. The implications for glaciology were revolutionary, that there was a melt-induced acceleration mechanism that was previously not included in climate models. We didn't appreciate that this physical process was happening. Right after I left University of Colorado and went to Ohio State, I focused on the melt lakes that form at the surface of the ice sheet. We targeted a number of lakes. We learned that this one contained 300 million cubic meters of water. And how we got at that number involved simply boating on this lake with a $100 fish finder from Garmin and just getting the water depths and comparing those with the satellite imagery on this and another lake, and realizing that there was a relationship that the lower the reflectance of the lake was, the deeper it was. The deeper waters are darker, and these fit lines allowed us to measure the volume of water from space. These lakes, they melt down and they find a crack, and the water goes, and you get a Niagara-type flow for a few hours, and a tremendous discharge of water to the base of the ice that produces an acceleration of flow. You get, for a short period of time, this is just over a 1 hour period, you get like a factor of 3 acceleration of the ice as the surface, this is the surface of the ice sheet actually is jacked up as this water is forced down under gravity to the bed. This is warming the ice in the interior. Warmer ice flows faster than cold ice. And so here's a physical mechanism that an increase in meltwater can soften the ice, make the ice sheet flow faster. This is an example of a physical process that's not in climate models, and why climate models repeatedly underestimate the sensitivity of these systems to climate. Let's go to North Greenland. This is Petermann Glacier. It used to be the longest ice shelf in the Arctic. In 2010, an area 4 times Manhattan Island detached in one single piece. We knew that this would happen because this rift was moving toward the front of the ice shelf and widening at the same time, so it became an elementary prediction. And this year, or 2012, it broke at the Big Kahuna, which is exactly there, and did, an area about 1.5 Manhattan's islands breaks away. This is the most retreated that Petermann has been in the period of observations beginning in the early 1900s. In addition to telling the story about changing glacier landscapes, we're applying feature tracking algorithms to measure speed changes on this glacier. And that revealed that the speed changes coincided closely with surface melt intensity. So this and other cameras, we proved that the flow sensitivity of these glaciers is quite strong. Even just to weather. Warm weather, it's flowing faster. Cold weather, it slows down. And it's meltwater production. So rainfall events would speed up this glacier. Very sensitive. This is something else we didn't really appreciate in the mid-90s. An important physical process has to do with the reflectivity of ice. And here, the leaf is absorbing more sunlight, it's heating locally, you get a little bit of meltwater and it expands, and you have a kind of a solar collector that heats the ice. And we measured this reflectivity using satellite data. Fresh snow crystals have jagged edges that scatters light back up from the surface. Melting crystals, more rounded, doesn't scatter light as much. An analogy also is with sand. Wet sand is darker than dry sand. That's true for snow. Wet snow is darker than dry snow. So these are physical processes that allow snow to trap more sunlight. And that produces what we call a feedback process. And this feedback really begins with an enhanced greenhouse effect on our planet, or anything that can increase temperatures. What increased temperatures do is make the snow and ice less reflective, and that actually in turn can increase temperatures because a lower reflectivity surface absorbs more sunlight, and that's adding more heat. So this is a positive feedback here. If increasing temperatures, as we understand, increases wildfire, that releases soot into the atmosphere, darkens the snow and ice. That also contributes to heating. So we're tracking different feedback processes that produce an amplified climate change. And not all of these physical processes are in climate models, which is why climate models often surprise us at how conservative they are in predicting climate. A good example is climate models far under-predicted the rapidity of Arctic sea ice decline, because the models just don't have all of the physics. The scientists haven't fully articulated all of the physical processes and coded them into climate models. It just hasn't happened yet. And if anything, the climate models are just too slow. So we're tracking the reflectivity of Greenland. Here's a number of years. The black line is 2012. You can see the red line is 2011. Here's like 13 different summers. And what's normal is the reflectivity drops in the summertime because the surface is heating. 2012 was exceptional because it was the lowest reflectivity in the record. And it was also the warmest summer on record. So it wasn't, it didn't really take much to prove that this low reflectivity was driven by heat, but it was also a heavy fire season, and that question of the role of soot in the reflectivity decline is still kind of an active field of science, if you will. We want to go back to Greenland and measure soot concentrations simply by coring down like 6 feet into the snow, get back down to the 2012 melt layer, bring back those samples to the lab, measure the soot, and that's just part of the story. And the lowest point is, let's say, 65% reflectivity versus 70. So 5% reduction in peak summer reflectivity of the ice sheet corresponds with an additional absorbed solar energy equivalent with twice the US annual energy consumption. To try to put it into context, it's 100 exajoules more energy being absorbed by the ice sheet in summer. And the effect of that was to double the melt rate. And we published this in the Cryosphere, which is an open access journal. Anyone can download that. And this is the ice sheet responding to a perturbation. It's responding to warmer temperatures, and maybe fire is part of that as well. I suspect that fire is a minor part of the story, but it's probably part of the story. The change in reflectivity is strongest in the lowest elevations, because that's where the melting exposes bare ice, just at the lowest elevations. So that's where the biggest changes are. That was that decline in reflectivity at the highest elevations of the ice sheet. This is where there's not much melting. We used to call this the dry snow zone, but in 2012 we got complete surface melting. And we saw that coming, right? You saw that in the video. We predicted that in this publication. And it was an elementary prediction because there was no longer any cold content left in the snowpack. It only would take a normal summer to bring it to the melting point. There just wasn't that energy buffer remaining. So we actually, you don't normally put a prediction like that in a science paper. It's speculative otherwise, but it wasn't speculative because the energy budget showed there wasn't any cold content left. It was right at the melting point, and it happened in the next possible year. We were fortunate that Greenland has some of the longest temperature records on Earth. It's surprising, perhaps, but the Danish Meteorological Institute has been operating a number of stations around Greenland since the 1800s, just like in Europe. We're used to the longest temperature records coming from Europe or a few other places like Tokyo, but we have long records from Greenland, and this is the summer temperatures in Greenland. And the records are so long that you actually have the end of the Little Ice Age here. And before the Little Ice Age, it's kind of off and on, starting in the year 1250, roughly, up until, say, 1850. That's the Little Ice Age, an extended period that coincided with the Dark Ages. And, you know, it's hard to live in a cold climate. I don't mean to say that's easy when it was cold, because they had Dark Ages, they had famine in Europe in the Little Ice Age. We have the warming coming out of that, and this is this kind of global warming pattern that's particularly strong in recent years. And all that satellite data I showed you was just from this period. The longer, this gives us that long perspective we can put that short satellite record into. And based on this, the fact that the Little Ice Age goes before here, the recent temperatures are warm. Temperatures have not been that warm in about 860 years in Greenland. That's the previous time that was the medieval warm period. That's when the Norse settled Greenland. So the recent years, these are interesting times. I mean, we started publishing this stuff like back here, and it was like, oh, the 1920s are just as warm, you know, like, and climate change skeptics rightly said, well, it was that warm then. I mean, what's the big deal? But now the signal's starting to punch out above that, and the skeptics on that point have gone silent, rightly so. Ice core records give us a temperature estimate going back thousands of years. And this one is, I think, is quite accurate because it compares well with the reconstruction that I showed you earlier. And this is using trapped nitrogen and oxygen in bubbles in the ice. It's not an isotopic temperature, it's actually a bit more direct. Anyway, this just reinforces that the recent temperatures are probably the warmest that they've been in about 800 years. This is like the last part of the medieval warm period. So here's your little ice age, and especially in this period. And the red line is the 24 years of instrumental data that we have. This is from the summit of the Greenland ice sheet. And so we've put together the instrumental record, 24 years of data. And you can see it's quite a strong warming during that short period of time. But we need that longer term perspective to put the recent changes into that context. All of this has produced a net mass loss of the Greenland ice sheet that's doubled. In the first part of this record, this is from 2002 to say 2006, Greenland ice sheet is contributing 0.5 millimeter per year to global sea level rise. And at the end of the record, it's doubled. It's been shown through other independent work that when perturbed like this, ice sheets, it's useful to measure their sea level contribution not in linear terms, but in doubling times. And the doubling time for Greenland is approximately 10 years when perturbed, like it is when it's warming like so. And so this study, really clever statistical reconstruction of sea level globally, it has the instrumental record here in black from tide gauges. It goes back to like the 1860s or so. And then this sea level reconstruction is based upon shoreline datings and corals and, a variety of pre-instrumental data. But it's pretty amazing. It resolves the medieval warm period and the little ice age. The sea level drops globally about 20 centimeters. That's because the ice was growing in the Alps and on the ice sheets in Arctic Canada, etc., Alaska. Glaciers were growing at this time. And then the ice starts to lose its mass up to the present. This study also includes what we think is our best guess for the next century for sea level, and it looks like that. This is what we call the hockey stick pattern, because it's going along like this and bam, it goes like that. The hockey stick has been hotly contested because of the implications are that human activity is driving abrupt climate change. And we're just seeing the beginning of that. And so the hockey stick has been under fire, but now hockey sticks are emerging not just in sea level, but in, originally in temperature data, but in precipitation records, in a variety of independent sources of data now confirm the hockey stick is real. That was what we used to think sea level would be at the end of the century, about 0.5 meter sea level rise by the end of the century. But once that first epiphany in glaciology with the moulins and the water pouring down, that melt-induced acceleration, when you put that into a model of ice sheets, you get this kind of sea level rise. And that's a more credible number at this point. 10 years ago, that's what we thought sea level rise would be at the end of this century. Now we think it's going to be this. And I'll come to it later, that it's highly uncertain. We can't tell you with much confidence that sea level is going to be 1.5 meters higher at the end of this century. And the reason we can't tell you with much confidence is because there's a lot of other physical processes that haven't been built into the models yet. We shouldn't really trust the models to be, are they too conservative, the models? Probably. And I'll show you why. This is a hockey stick in atmospheric chemical composition that's driven by greenhouse gases. We've got carbon dioxide that's 40% above the peak values of the last 125,000 years. Longer than that, but I'm comparing, anyway, methane is 200% above normal. Other greenhouse gases are elevated. This is the impact of all of the good things that have come from industrial output in our civilization. And we have to credit all of the engineers and scientists that have given us lights and auditoriums and projectors and all of these great things. And these are good things, right? These have made our lives better. But we have externalized the cost of that on our environment. That's not incorporated in our economic models. And this is the impact. And we're just starting to come to terms with that. And we don't have to judge that as political. It isn't. It's just the chemistry of the atmosphere. And it happens to affect our climate. And here's the real shocker, is that when you connect the dots, you realize that at current atmospheric CO2 concentrations, for climate to be in equilibrium with 395 parts per million, that's today's value, the global sea level has to rise 69 feet. That's just to be in equilibrium. So we're already committed to 20 meters of sea level rise. And it's obviously going to take more than 100 years for that to happen. But where we are at the end of this century, when some of us in this room will still be alive, is somewhere, you know, I don't know, is sea level this or is it higher? That's where we'll be in some decades. And this is already, this isn't actually controversial. This is something that scientists don't often talk about because of the large uncertainties involved. I mean, who would connect dots like this on a curve? There's only a couple data points there, right? It's not very credible. Well, we have 100 meters of sea level change between the Ice Age and now. And you know, if you've ever been to Scotland or Norway, you can see the old shorelines way up on the valley side and so on, that actually the ice is removed and the land has gone up. Sea level is complex, but these data are credible. So the implication is that we've committed to already a lot of sea level rise. If we maintain atmospheric CO2 at this elevated value, and many have called for 350 as the target. We're at 395 now, and when we cross over 400 in the next couple of years, you're going to see a lot of headlines about that, because philosophically crossing 400 is going to be kind of a big deal. And it's going to be a reminder to us as each year 2 parts per million more, and it keeps going forward. The real story with global climate change is about oceans, because oceans cover 7/10 of the planet's surface. And the ocean heat uptake, which is where 8/10 of this heat is going, it's going into the oceans. We see a bit of temperature rise on the surface in the atmosphere, but it's the oceans that are absorbing this heat imbalance of our atmosphere is heating up, and because the planet's mostly ocean covered, the heat's going into the oceans primarily. So this adds up to enough, this amount of energy. It's okay, 10 to the 22nd joules. I hate to say the statistic, but it's true that this energy imbalance today is equivalent to 2 little boy Hiroshima bombs per second energy going into the oceans. That's the energy imbalance because of 40% higher CO2 in the atmosphere. We see in Baffin Bay, for example, this is just west of Greenland, since the 1920s, warming at depth into the ocean. This is relevant for the glaciers, because the glaciers actually terminate into the water, and they're melting from below. And I think I'll get to that. I'm kind of racing through this material a bit. Sorry for that. I wanted to come back to the hockey stick here. This is really where the hockey stick story first came out, is with temperature records. And so you have your instrumental record. These are data in red. These are weather stations that have been operating since the 1880s, continuously at hundreds of locations around the planet. So that gives you this red curve. That's the measurements, and it shows warming. When put into the context of the last 1,800 years, you can see how steep that warming is. And here you see the medieval warm period, again, the Little Ice Age, and the hockey stick. This is abrupt climate change that has already been underway for a few decades, that we're just beginning to appreciate now. This is context. I wanted to get into a little bit of history and politics, because fundamentally this is a human issue. James Hansen testifies to Congress in 1986, saying, this is NASA's top climatologist saying, guess what, we have a problem. He's been called the Paul Revere of climatology. He's sounding the alarm and saying, Congress, we have a problem. We have too much greenhouse gases in the atmosphere. We have to dial that back. It's going to overheat the planet and make weird weather, etc. This science is not new. He published this graphic which illustrates pronounced warming in the higher latitudes. This is a global map. It's kind of hard to see. There's Greenland. This was actually just the changes from the data from 1880 to 1985. And there had been already a 3 to 5 degree temperature change at the high latitudes. We call this Arctic amplification. Because of albedo, the reflectivity, that feedback, that multiplier, melting snow absorbs more sunlight and warms more. That's what you see in the data here. So James Hansen was well aware of this, and primitive climate models from the 1960s predicted this. This was not new science, it's only been confirmed. And here's just a recent year, 2012, and we see this pattern of high latitude warming. And this is recurring year after year. And we've learned that the Arctic warms at twice the rate of the lower latitudes. And that's because of the reflectivity feedback with temperature that we've looked at. That's exactly why you get this pattern of, so yeah, maybe it's warmer down here, but it's a lot warmer in the Arctic, and especially in the high Arctic. So we actually have a choice here. This isn't just like hopeless. Glad that the lecture was on the ground floor of the building. We have a choice. We can dial back the CO2 emissions and have a less warmed climate, or we can pretend that it's not an issue or that it's a hoax and just go on business as usual when all the data are at the present time, 97 out of 100 climatologists say that global warming is real. 2 are undecided. 1 says it isn't real. It's kind of like having 97 dentists tell you you have a cavity that needs to be removed, and one out of 100 says, don't worry about it. What do you do? 97 scientists say you have, or doctors say you have cancer, 1 says you don't. What do you do? I mean, so that obviously, if you're a policymaker, you say, okay, the policy is going to be to reduce CO2. And so James Hansen finds himself being arrested in front of the White House, protesting the Keystone XL pipeline. Because as far as Hansen is concerned, if this pipeline is leaked, it's game over. There's enough carbon in the Athabascan oil sands in Alberta to bring atmospheric CO2 well above 450 parts per million. And Hansen, who arguably knows better than anyone in the US, is risking his credibility. Engaging in a peaceful, nonviolent civil disobedience action, the largest in a generation, at the White House. And he wasn't alone. There were 1,252 other people, including people of faith. This was a transgenerational sit-in. There were young people, old people, participating in this very powerful demonstration of trying to force Obama, do not permit this pipeline. If that pipeline gets built, that locks us into 50 more years of oil addiction. We can't let that happen, was their message. And the story is continuing to come up. It's President's Day, I think it's the 17th of February. People are going back to the White House to send this message again to Obama, to try and pressure Obama not to cave into the most wealthy industry on the planet from fossil fuels that are profiting record amounts, making more money in the history of money. That's what this kind of David and Goliath battle seems to be about. I would argue that to avoid the carbon bomb, we need to develop clean energy, low carbon energy. We're not going to move back to the caves, but we need clean energy, domestic energy, and et cetera. You know, and that's an issue that's not really political. People tend to agree that it's not that our current energy policy needs some reform. I think it comes down to this, that our economic system does not internalize the costs of development. That we pay, say, 10 cents a kilowatt hour for coal electricity, 10 cents a kilowatt hour, when the true cost of electricity is paid by the environment. And okay, we pay 10 cents a kilowatt hour, but there's economists call it externality. We do not internalize the true cost of our economic development. And the year that this statement was made, sustainable development was defined. Development that meets the needs of the present without compromising the needs of the future. When was this statement coined? Does anyone know? 1987. This is a new concept. We have to develop in ways that don't compromise future generations. We weren't thinking like that 20 years ago, 30, 40 years ago. But that's been the epiphany that we have now. It's like, oh, hang on, we can't compromise our children's future access to clean air and water. We have to preserve that. We have to internalize our economic energy policy, for example, because it has such a profound atmospheric chemistry link. And if we do that, we can reach sustainable development. That's the challenge to this generation. And the ice sheets are just a useful indicator of that change. I guess that's the good news, that we know what we need to do now. And that concludes my presentation. Thanks for your attention.